find d squared d theta squared. All right, notation, what does this tell us? Second derivative of theta arctangent theta. Is it okay that it uses theta instead of x? Yes, no problem. This tells us to do what? Evaluate at theta equals 1. So first find the second derivative, then plug in 1. Don't plug in 1 and then take the second derivative, because you'll get 0. All right, so our options are 1/5, 1/4, 1/3, 1/2, and 1. And the result is a half. All right, so to take the derivative, first start by taking the derivative, product rule. So you have the derivative of theta is 1 times arctangent. Theta times derivative of arctangent, well, our derivative of arctangent is 1 over 1 plus theta squared. So now to take the second derivative, take the derivative of the first derivative. Derivative of arctangent is 1 over 1 plus theta squared. Now you need to do a quotient rule. Low d high minus high d low over the low squared. Well, it turns out when you plug in theta equals 1, you'll get 2 minus 2, which means this term goes away. You end up with just 1/2. So the answer is a half. All right. Great. Any questions on that one? Well, we have more fun problems coming up today. In fact, today is, well, I don't want to ruin the surprise. All right, so before we start, our thought for the day. So, in the past, I have made no secret of my disdain for Chef Gusteau's famous motto, anyone can cook. But I realize only now do I truly understand what he meant. Not everyone can become a great artist, but a great artist can come from anywhere. Anton Ego. Does anyone actually know where this is from? Okay, good. All right. We have a class which has sophistication and good taste. I like that. So, I like the end in particular here. A great artist can come from anywhere. And I think that oftentimes we start making assumptions about people, and sometimes we even make assumptions about ourselves. We look at someone and say, you have this characteristic. Maybe you're from a particular country or particular race or gender or something, and we start making assumptions like, you must be good at math. You must be bad at math. And I think that's dangerous to do, because I've worked with lots of people in mathematics. I've all types, many different countries, different continents. I don't know if I've worked with anybody taller than me, but beyond that, just think people very similar, people very different from me, and I've appreciated all that they can do. So keep in mind, math is meant for everyone, including yourself, because you might be looking at this and saying, oh, this is a very depressing quote, Steve, because it says, not everyone can become a great artist. So I took a class when I was a student. We still had college back then. And I took a drawing class when I was an undergraduate. And our instructor was actually bigger than me. He was a tall guy. He played basketball. He's also from Africa. He had a wonderful accent. And on the very first day, it's like one of the very first things he told our class. He said, I do not believe you can all become good artists, but I do believe you can all become good draftsman. And what he was trying to tell us was like, look, not all of you are going to become artists, but all of you can become capable of doing the basics and be proficient in the basics. I think it's true for us. Not everybody here is going to become a mathematician, but that's okay. All of us can become proficient in math. All of us can become, as my teacher said, good draftsman. All right. So, thought for the day. All right. So, today is a lovely day because we only need basically one idea. And then it's just problem after problem after problem. Related rates. And so what does this mean? So related says there's a relationship going on. So there's quantities, variables, whatever you want to call them, are related by some equation. Now, when we say the word equation, what we're looking for is something with an equal sign. So something equals something. That's what we mean when we say an equation. So we say, okay, look, if the quantities are related, then the changes or the rates of change of the quantities are also related. In other words, their rates are related. And so, okay, so how do we find the relationships between their derivatives? Well, we look at it and we have a thought. We say, okay, the key thing is to say everything depends on some variable that we usually don't see at all. We think of it as time. So maybe our relationship connects X and Y together. Say, all right, well, great. But now there's a hidden variable T that says, okay, X depends on time, Y depends on time. And now, since things depend on time, we can say, take the derivative of everything with respect to time. Much like what we would do if we were doing implicit differentiation. In fact, there's a very, very serious overlap. Similar ideas going on. So, what's the process for related rates? Well, we're going to be given a word problem, and so there's going to be a lot for us to read today. And the teachers love these problems, by the way. If you don't believe me, if you look at the handout and you flip it over, you'll see it's packed with problems. It's so packed, I ran out of space. I had to cut to fit it all in. So they love putting these problems on exams. So it's one of those things where it's like, you want to make sure you get this down. So what's our process for the word problem? Well, we find a relationship for the quantities we are interested in. How do we do that? Usually involves drawing a picture. Doesn't always, but it's a good place to start. Look for a couple of key things. Pythagorean theorem, they love Pythagorean theorem. Very popular. Similar triangles, very popular. And we'll see examples of that. They look for things like area formulas, volume formulas, more or less very basic things. You have to practice, but nothing too surprising. Once we found our relationship, our equation, if you will, take the derivative of everything with respect to time. Use your chain rule. And if you're taking the derivative of x with respect to time, what's the derivative of x with respect to time? dx dt. Once you've done step 2, plug in what you know, solve for what you want, and we're done. So that's the idea. So that's the theory. The rest of the day is practice. Are there any questions? And I think that as we go, we'll get better at understanding. All right. Well, let's do some practice. So, first problem. A 10-foot ladder is leaning against a wall, and the bottom of the ladder is currently 6 feet away from the wall and sliding away from the wall at a rate of 2 feet per minute. How quickly is the other end of the ladder moving down the wall? All right. So you'll notice there's not a lot of math here. There's a couple of numbers. So that's something we can hook onto. I see a 6 feet here. I see a 2 feet per minute there. So there's something. Now, about this problem? Oh, I should have circled the 10-foot. What are some things about this problem that would say you're looking for related rates? Well, it's giving you one rate. Yes? See, that's 2 feet per minute. That's a rate. And what is it asking you to do? Right, it's asking you to find another rate. Because it's, how quickly. Quickly is secret code for change. So you see one rate given, and it's asking you for a different rate. So you're like, oh, these rates should somehow be connected. So when you see rates given and rates that you're looking for, then you say, I should put on my related rates hat. All right, so step 1, draw a picture. Now, you could say, look, I'm going to be very precise about my picture. All right, I'm going to draw my ladder here. It's going to look very realistic. Now, is this a helpful drawing? Well, it's nice. It's a pretty drawing. It certainly looks like a ladder. However, it's probably not the most useful way to represent what's going on. So this is almost, I think one way to phrase it is, you don't need to go for realism. It's better to do abstract. Really capture what's going on. So let's just, instead of drawing this, we'll have, here's the floor, here's the wall, here's the ladder. Which one will be easier to think about? I think the abstract is a bit easier. All right, so the next thing is to start thinking about labeling things. What's changing? What's not changing? Well, it's telling us about how we're moving away from the wall. So this is something that's changing, the distance to the walls. So if something is changing, it needs to be given a variable name. What would you like to call this?
The rate of fall?
What name would you like to call this? X seems like a very reasonable name. Do you have to call it X? No. If you don't call it X, your grader will say, why didn't you call this X? X is such a good name. What else is changing? Or if you like, what's another rate you're trying to find or that you've been given?
The rate at the top of the ladder is going up.
Yeah. So I can think of it as I have this measurement, which is how high up it makes contact with the wall. What is that? What should we call it? Well, we need to give it some name. That's why. Oh, you mean call it the variable y. Classic Steve mistake. All right. All right, is there anything else we can label here? For instance, what about this length? 10. Now, do we need to give it a variable name? No, because it's not changing. It's just a ladder. It's always 10 feet. Well, looking at our setup, can you think of anything which connects these three items? X, Y, and 10. Right triangle, right? Pythagorean theorem. So what do you have? Pythagorean theorem, x squared plus y squared equals 10. All right, so this is our relationship. This is, in some sense, the hard part. You have to translate the problem into the relationship. Now let's do a few other things. This quantity here, how do we interpret it in terms of how we've written things down? What does 6 feet away represent? X. So we're given x equals 6. What about this one? It's a rate. So if it's a rate, it's a derivative. What derivative is it? Is it dx dt or dy dt? Dx dt. So dx dt is 2. That's what we're given. What is it we want to find? We want to find dy dt. How quickly it's moving down the wall. So now we essentially can ignore all of this. We've got our relationship, we have our givens, and we know what we're looking for. So this is a translation. This is the hard part. And it just takes practice. All right. What comes next? We've done step 1. We found a relationship. What's step 2? Take a derivative. So remember, what we're thinking of when we think of related rates, we're saying, in our case we have x and y. So we're thinking of x as a function of t and y as a function of t. And we're in calculus, in particular calculus 1. And at this point, there's always in the back of our mind, should we take a derivative? Seems like a good idea. Derivatives seem to show up a lot. Okay, so let's take the derivative. Taking the derivative with respect to t, what's the derivative of x squared with respect to t? Someone said 2, okay. I'll write down 2. 2x dx dt. Where is the dx dt coming from? Yeah, because this is our thought process, we normally don't write it out, but we could have. This really says x of t squared plus y of t squared equals 10. And so we're taking the derivative of that. So it's the chain rule. The 2 comes down, x of t to the 1, that's the x, times the derivative of the inside, and the derivative of x of t is dx dt. Okay, what about the derivative of the next term, y squared with respect to t? What will that be? Two y dy dt, very similar idea, equals, I take derivative of both sides. Does it equal 10? Yes? No?
Yeah.
0. Why 0? Yeah, because you have to take the derivative of both sides. Derivative of a constant is 0. Okay, all right. Cool. So we took our relationship, took our derivative, and now this is a relationship for the rates.
Could we also write like x prime instead of dx over dt?
You could, as long as you understood what you meant by x prime, and it was clear.
Okay.
All right, so what comes next? So we found a relationship in step 1. Step 2 is to take a derivative, and then there's one more step. Yeah, plug in what you know. Solve for what you don't. Okay, so what do we know? We know x, we know dx dt. So here we go, plug in. 2 times x times dx dt plus 2 times something dy dt equals 0. Now I left a gap here. Do we know why? It wasn't given explicitly in the setup, but do we know it? We can use the relationship to get y at the point we're interested in. So we know x is 6. 6 squared plus y squared is, 10 squared? 100. All right. Well, 6 squared is 36. Y squared then is 100 minus 36, which is known as 64. So what does y become? 8. So we can extract what y is from our relationship. Now we're after dy dt, so we move things around. 2 times 6 times 2, that's 24. We'll move to the other side. So we get 16 dy dt is negative 24. So dy dt, negative 24 over 16. Common factor of 8, negative 3 over 2. Now, I will tell you that most problems, they like to say, include units. So let's include units. What are the units? Feet per minute. Now, how do you figure out your units? Well, you think about what does y represent? Y is the measurement of feet. What is t? Measurement of minutes. So feet per minute. And there we go. Now, is this reasonable? Do we like the fact that we got a negative number? Does that make sense that it's a negative number? Because what should be true? Logically, if we're sliding down, so if x goes a little bit further out, then we should be, as x moves further from the wall, then the point of contact should move down the wall. So that's actually good that we got a negative number. It's always nice to sort of check, is this a reasonable answer? All right, so there's our first problem. You always remember your first related rates problem, because it's almost always a ladder problem. Just tradition. Start with the ladder, and then work your way up. Any questions? All right. Let's see. All right. Like I said, it's all practice for the rest of the day. Okay, so you are 10 kilometers away. And by the way, if you do have the handout, this is number 3 on the handout. You are 10 kilometers away from a rocket launch, close enough to hear it, but not so close to be instantly vaporized. That seems like a good distance. You are filming the rocket as it goes up. Given that the moment your camera forms an angle of pi over 3 radians with the ground, that the angle is increasing at a rate of 0.2 radians per minute, find the speed of the rocket. All right. So we should draw a picture. Now, if you like, you can, of course, channel your inner artist. So we can draw our rocket here. This is definitely not going to be to scale, by the way, by the time we're done. All right, so there's our rocket. And here we are filming it. This is us. Do we have that distance? 10 kilometers. Yeah, that's fixed. All right, now we have the rocket. Say, all right. Now, is this distance fixed for the rocket? Oh, it's going up. So we should give it a variable. In fact, we are very interested in this. Why are we interested in this? Because it tells us to find the speed of the rocket. It's how the rocket's going straight up. So we're interested in this rate of change. And I didn't do this beforehand. I should have pointed out, how do we know this is a related rates problem? We're after the rate of the rocket. We're given a rate of something else. So if you are given a rate and you need to find a rate, related rates. What do you want to call that height of the rocket? What? X or Y? Y, okay, all right. Sure. And now, we'll finish up a triangle because we love triangles. That's just our jam. What's our other thing we want to throw in there? The angle. So notice, we're not going to throw in the Pythagorean theorem. We're going to figure out what the problem tells us. It's forming an angle. Okay. So, here's our angle. Again, someone said, that should be 60 degrees. It doesn't look like 60. You are correct. But that's okay. Now, we have our picture. The two things which are changing have been marked. We're given information about how theta changes. We're after how y changes. Look at our picture. What relates theta with y? If you have a triangle, what sides do we know anything about, or can we say things about? Adjacent, opposite. So channel your inner SOHCAHTOA. What connects opposite and adjacent? Tangent. So, tangent of theta is y over 10. This is our relationship. All right. We should also talk about what we've been given and what we need to find. So what are things that we've been given? We were given that there's an angle of pi over 3. So theta is pi over 3. Is there anything else that we're given? Right. So there's an angle, and the angle is increasing. Increasing is code for derivative, or so is rate. So we have these phrases. We look for a derivative, 0.2 radians per minute. So this angle increasing our rate of 0.2 radians per minute, how do we write it in our notation? d theta dt, how the angle is changing, is equal to 0.2. Is there anything else that we've been given in terms of our picture that we haven't marked yet? But we don't have x in our picture. Yeah. But since that's not varying, it is important to help us get our relationship, but we don't need to worry about it in terms of a evaluation. What is it we're supposed to find? dy dt. Okay, so we have our relationship, we know what our givens are, and we know what we're after. So, what comes next? Take derivatives. So we're going to take the derivative with respect to time. So taking the derivative with respect to time, derivative d dt, derivative with respect to time, derivative of tangent theta with respect to time. So when secant squared, derivative of tangent secant squared. Anything else? Chain rules. Don't forget the chain rule. It's the chain rule. So I think someone said d theta dt. So as you take derivatives, you're always going to get these partial derivatives. Equals, what's on the other side? The 1/10 is a constant. Derivative of y with respect to t. Derivative of y with respect to t, dy dt. All right. Well, cool. So, we're ready to plug stuff in. Plug in. We have secant, all right, this says pi over 3 quantity squared. d theta dt is 0.2 equals 1 over 10 dy dt. Do we know secant of pi over 3? This may not be one you frequently memorize. Do you know cosine of pi over 3? 1/2. So if cosine of pi over 3 is 1/2, what is secant of pi over 3? 2. Flip it over. So this becomes 2 squared times 0.2. Bring the 10 across times 10. That's your dy dt. Well, we can clean that up. What's 2 squared times 0.2 times 10? It's 8. All right. 8 what? What will be our units? And how do we know those are our units? What should y be measured in? It should be kilometers, because you want to compare these two. This is 10 kilometers, so this should be kilometers. So units of y, kilometers. Units of t, minutes. How do we know it's minutes? Because of this part right here. 0.2 radians per minute. So it's telling us the time. It says we're measuring time in minutes. So 8 kilometers per minute. So that's good. It's going up. We would be nervous if we got a negative answer here. That's a bad sign. But it makes a great YouTube video. Bad sign. All right. Any questions? Okay. Well, looking at our time, I want to make sure. All right, I'm going to go through this one a little bit quicker. Unfortunately, I don't think it's on the handout, but you grabbed a water cup in the shape of a cone next to the water cooler to get a refreshing drink. Well, that's very good of you. You should stay hydrated. All right, so what does this look like? Well, that's your water cup. It looks like a cone. And in case you're wondering, you would have the tip pointed downwards. So after filling it, so we now have water in this, you discover there's a hole in the bottom. Oh, see, there's this exclamation mark. Ah! Okay, so water is coming out. So, given that the cup is 4 inches high and 3 inches across at the top. So we have that this is 4 inches. This is 3 inches. The water level is currently 2 inches. Okay, so the water is not completely full. It's currently 2 inches. And it's dropping at a rate of 1/2 inches per minute. Then how is the volume changing? Now, in case you're wondering, the volume of a cone is 1/3 pi r squared h. We would give that to you because we like you. All right. So, the water that's in here is the shape of a cone. So it's like, all right, we just need to figure out what's happening. So as the water drops, does R change and does H change? Well, not for the whole cup, but for the part where the water is, the water level is dropping. That says the H is changing. As H drops down, the radius for the water will also drop. So R and H are both changing. Okay, so there's a fair amount changing here. All right, so what do we need? Well, let's slice it. So this is a common idea. And say, look, it almost looks like triangle. We love triangles. Related rates loves triangles. Slice. Slice. Okay? So, when we slice, we get this picture. Now, what's the relationship between this triangle versus that triangle? So the one where the water is versus just the whole cup. They're what? They're similar. Now, similar has a very particular name. What does similar mean? Or I should say, similar has a particular meaning. When we say two triangles are similar, what does that mean? They're connected by scaling. So if I scale the small triangle, it'll look like the big triangle, and vice versa. I can scale down the big triangle and get the little triangle. So, for convenience, let's cut it in half. Here is R. Here is H. So R and H, that's for the water portion. In the big triangle, what does the corresponding measurement for H turn out to be? 4. What does the corresponding measurement for R turn out to be? 3/2 or 1.5. All right. So, the great aha says that ratios will stay the same. And the reason ratios stay the same is because you're taking a division of two things. And if you're scaling top and bottom by the same amount, the scaling factors cancel. So, for the small triangle, R is to H as, for the big triangle, 3/2 is to 4. Or, put another way, R equals 3/8H. So we have a relationship between R and H. So they basically move together in a very predictable way. Now, let's look what we want. We know the water level is 2 inches. Is that an R measurement or an H measurement? H. It's also dropping at a height of 1/2 inches per minute. So, we're given that H is 2, dH dt is, I was anticipating someone would say 1/2 and be like, is it? Is it? In as high a pitch of voice as I can with my current throat. Is it? Negative 1/2. Why is it negative? Because we're going to drop it. Dropping like it's water. Dropping it. So, it's going down. So, that should be negative. Have to pay attention to your signs. What is it we want to find? How is the volume changing? Changing is code for derivative. So we're after dV dt. So, what would be ideal? We want to somehow connect what together? We want to connect volume to height. Because those are the changes that we're trying to connect. This currently gives us volume in terms of R and H. We'd like to get rid of R. Can we get rid of R? Yes. We can replace R in terms of H. So, we'd like to have volume and H be our variables we have left. So volume is 1/3 pi. R is 3/8 H squared H. Well, if you simplify this, this becomes 3/64 pi. So just 9/3 is to 3. H squared is 64. And then there's an H cubed. So this is our relationship connecting volume to height. We use similar triangles to figure out, hey, how does R and H relate? So I can get down to a simple relationship between V and H. So, are we done yet? We have our relationship. Once we have our relationship, what do we need to do? Well, we don't plug in yet. What happens before we plug in? Derivative. So, we're going to take the derivative with respect to t. Derivative of v with respect to t. Yeah, derivative of v with respect to t is derivative of v with respect to t. The 3/64 is 3/64. The pi is pi. Derivative of h cubed with respect to t. 3h squared and dh dt. Okay, well, let's plug in. So here we go. We're going to plug in. We have 3/64 times pi times 3. I'll go ahead and put the 3 there. 9/64 pi. What is h? 2. So 2 squared. What is the h dt? -1/2. So we can cancel one of the 2's. 2 goes into 64, leaving 32. So you end up with -9 pi over 32. What will be our units? For volume, what's our units? How are we measuring things? Inches is a one-dimensional measurement. So for volume, inches cubed. So 9 pi, -9 pi inches cubed per downstairs. Minutes, seconds, hours? Minutes. How do we know it's minutes? Because it says minutes. All right. So let's try another one. I apologize. Any questions? So we've seen examples of volume, similar triangles. We've seen Pythagorean theorem. We've seen some trig. A particle is moving along the implicit curve. X cubed plus y cubed equals 9xy. Given that when the particle is at the point 2, 4, we have dx dt equals -2, then find dy dt. All right. Is this a related rates problem? Trick question. It's yes, because everything's related rates today. What tells you related rates? They gave you one rate. They want you to tell them another rate. So that's related rates. Do we have a relationship? Someone says, it's not in their head, yes. What's the relationship? They gave it to us. What? They're nice people? Yes. Oh, those math teachers. Such kind, generous souls. All right. So they gave us the relationship. What comes next? Take the derivative with respect to t. You'll get 3x squared dx dt plus 3y squared dy dt equals, product rule, 9 dx dt y plus 9x dy dt. Now what do you do? You found the relationship by seeing it was already given. You took a derivative. Last thing, plug in. What do we know? Yeah. We know x equals 2, y equals 4, and we know dx dt. So we have 3 times 2 squared, that's 4, times negative 2, that's dx dt, plus 3 times 4 squared, 16, dy dt, which we don't know, equals 9. Dx dt is negative 2. Y is 4. 9. X is 2. And dy dt we don't know. Well, 3 times 4 times negative 2 is negative 24, plus 48 dy dt equals 9 times negative 2 times 4 is negative 72, plus 18 dy dt. Move terms around. 30 dy dt, and you'd add 24. Negative 72 plus 24 is negative 48. So dy dt is negative 48 over 30. We can see they have a factor of 6 in common. So that's, we do better than 6? I think 6 is probably as good as we can get. Negative 8 over 5. Do we have units here? No, they didn't tell us units. So we're done. All right. So we didn't leave much time for your multiple choice, but here's a problem. A round aperture, it's a circular hole in a plate with a fixed radius of 2 inches. So here's our aperture, there's the fixed radius. Set up 10 inches from a bright light. It's casting a large disk of bright light on a wall that's 50 inches away from the light source. If the aperture starts to move away from the light source at a rate of 1 inch per minute, at that moment, what rate is the area of the disk of light changing? This is not really a problem to do in 1 minute. However, I think you can reasonably narrow it down to 2 choices in 1 minute. If you move this closer to the wall, just imagine moving it very quickly to the wall. What happens to the size of this circle? It shrinks down. So what should be the sign of our derivative? So which one of these can we rule out? So we can rule out those 3. So that leaves us with 2 options. Would you like to see it or would you like to think about it? The answer is A.